Okay, this is the first of 4 practice movies taken from PowerPoints. And if you haven't watched part 1, the molecular geometry lecture, you should do that because I'm going to be going through this fairly quickly, about 10 seconds per slide. But let me show you, this is actually would be the experiment, and I'll take you through the experiment. And there are several things that you're going to want to do in order for the successful completion of the experiment. And I'll go through those slides now. There are 2 slides that will explain everything you need to do for the experiment. Solve the molecular geometry of each particle. Formula of particle, approximate shape, total valence, total bonded electrons, total outer atom electrons needed to complete the valence. Show how the balance of the electrons are calculated. Conclude the totals, sockets, bonded electrons, and non-bonded electron pairs. Draw the final shape and include any non-bonded electron pairs. Calculate and insert the dipole moments. Determine the polarity. Draw a conclusion regarding bond angles if they are distorted due to asymmetry. Make a model using clay and toothpicks for each particle in the practice problems. I will check your progress during the experiment. So this practice set has 9 particles. Let's go over the names to make sure we're all on the same page. Phosphorus Trihydride, Iodine Trifluoride, the Nitrate polyatomic ion, Sulfur Tetrafluoride, Xenon Difluoride, Sulfur Hexafluoride, Aluminum Chloride, Nitrite, and perchlorate, those 2 polyatomic ions. So the first one is going to be phosphorus hydride. We want to come up with a basic shape, so we'll use the trigonal. You have 3 hydrogen atoms, so that makes sense at first. It may not be correct, but it's good at first. The total valence is going to be 8. Hydrogen just needs just has 1 electron available, and phosphorus 5. That gives a total of 8. We have 3 bonds that we drew in, so that's going to be 3 times 2 is 6. So we have those 6 electrons, and hydrogen requires only 2 electrons. So all valences are complete. And so we have 2 electrons left over, or 1 non-bonded pair to be placed around the central atom. So we have 4 sockets, therefore. We have the parent. Geometry is tetrahedral. We have 3 bonded, 1 non-bonded. That's going to be the shape. And now we are going to put in the dipole moments. And we see that phosphorus is just a pinch more polar than hydrogen. You can take that out a couple more decimal places if you're unsure. Trigonal pyramid, that's going to be the geometry, and we see that there's no bond symmetry, and so that we have polarity. That's absolutely definite. We have polarity. The next particle is iodine trifluoride. So again, we're going to have 3 bonds, and the central atom is going to be iodine. And now we're going to come up with the total valence, which is going to be 28, because we have 2 halogens, or 4 total halogens, 2 different types of halogens. So we're going to have, each one's going to have a valence of 7, that's 28. We have 3 bonds, that's 6. And then we will have 3 outer atoms, 3 outer fluorine atoms. Each needs 6 to make 8. So that's 18. So I'm going to subtract 6 and 18 from 28. That gives me 4, or 2 non-bonded pairs to be placed around the central atom. So that's going to give me total sockets of 5, 3 bonded, 2 non-bonded. The parent geometry is going to be trigonal pyramid, and the shape is going to be T. I look at the list. I look at the list and I see that it's going to be T. I put in the dipoles, and I see that the dipoles are going to be put in, and I have 2 that are going to cancel and 1 that's not, so I have no symmetry, partial symmetry, but not enough, and it's going to be, the polarity is going to be yes, I will have polarity. Now I have nitrate, so make sure that if it's negative, you're going to add an extra electron. So that's going to be my shape. We don't know if it's going to be trigonal, planar, but that's the best you can do with the information you're given. So I'm going to have a total valence of 24. Notice I have 1 extra. If you have that negative sign, that means you have an additional electron. I have 3 bonds. That's going to give me a total of 6 for the bonding. And I'm going to have 3 outer atoms of oxygen. Each is going to need 6, so that's 18. So that's going to give me 24 minus 6 minus 18, which is 0. So I have 0 non-bonded pairs to be placed around the central atom. So the parent geometry is trigonal planar, and that's what it's going to be. So the geometry of nitrate is trigonal pyramidal. However, you have to notice that the nitrogen is a non-metal, so it has to have 8 electrons. So it's going to need 2 more electrons. So it says in the note. So it says in the note, when the central atom is a non-metal, it must have at least 8 electrons. So 2 oxygen electrons are shared with the nitrogen. The double bond is treated as a quote-unquote single bond. And because the nitrogen has 0 non-bonded electrons, the geometry will indeed be planar. So you're going to have that 1 double bond there. Some of the bond angles might be a little bit off, but it will be planar. The oxygen is more electronegative than the nitrogen, so you're going to have the dipoles put in. Notice this particular note. It says the angle A is slightly larger than 120 degrees, and angle B is slightly less than 120 degrees. That's the influence of the double bond. However, that's not enough to change the fact that it will be planar, and you will have bond symmetry, and you will not have polarity. So the polarity is no. Sulfur tetrafluoride is going to be SF4. So you'll make it look like kind of a tetrahedral shape, because you have, that's all the information you have. You're going to come up with the total number of electrons, which will be 34. And then we're going to start. We have 4 bonds. That will give us a total number of electrons of 8, because you're going to multiply 4 by 2, and that will give you 8 total bonded electrons. And then we're going to have 4 fluorines. They're the outer atoms. 4 times 6 is 24. So we're going to subtract those values, and you get 2 left over. So you're going to have 1 non-bonded pair to place around the central atom, and you're going to have 5 sockets. So it's going to be trigonal bipyramidal, and you're going to get this kind of funky shape. that you're going to have. And you're going to look that up. You're going to look that up on your sheet. But first, let's take a look at this note. It says there are 5 sockets on the central atom, 2 polar, 3 trigonal. The socket which contains the non-bonded pair of electrons is a trigonal socket. Now you want to look up on your sheet. You have 5 sockets, 4 bonded and 1 non-bonded pair. And you'll find that that's going to be seesaw. Remember, the parent geometry is trigonal bipyramidal, 5 sockets. So now we want to look at the dipoles. Clearly, the electronegativity of fluorine is greater, so the direction of the dipole is going to be towards fluorine, which has an electronegativity of 4, compared to that of sulfur, which has 2.5. So we're going to put those in around the molecule. So that's going to be no bond symmetry, and clearly it is a polar molecule. Now, let's look at xenon difluoride. I'm not even going to talk because we've kind of already done this in the practice problem, but try to do it yourself and see if you can come up with the same answers as we do it quickly. Don't forget to have your sheets. You should really memorize that sheet. It's not very difficult. Remember, learning doesn't take place in a vacuum. If you don't know anything, you can't think about it. So have that sheet by your side. So you have 4 bonded electrons total, 2 bonds times 2. You have 2 outer atoms, which give you 12 total electrons. So that will give you 3 non-bonded pairs to be placed around the central atom. Remember, you're going to put them around the trigonal section of the shape. So you're going to have the parent geometry is going to be trigonal bipyramidal. 5 sockets, 2 bonded, 3 non-bonded. There you have it. That's your shape. You go to your reference sheet and you put in what you think the shape is. There are 5 sockets on the central atom, 2 polar, 3 trigonal, etc. So you can read that again. There's my electronegativity. I like to get that done before my geometry identification. Now I'm going to put my geometry is going to be linear. Remember, the parent geometry is trigonal bipyramidal. Put in my polarity, and yes, I have bond symmetry. No, it is not polar. Now let's do sulfur tetrafluoride. So I'm going to have 6 bonds, and it's going to look like that. I have no idea what that is. I'm not very good at art, so that's what I'll do. And if you look closely, you can kind of come up with a geometry, I suppose. So I'm going to have 48 total electrons, which is amazing, really. So I have 6 times 2 is 12, and I have 6 outer atoms times 6 is 36. So I have 48 total valence electrons. I'm going to subtract 12 and subtract 36. I have 0 left over. So therefore, I'm going to have 6 bonded, 0 non-bonded. I'm going to be, parent geometry is going to be square-based bipyramidal, and that's going to be the shape. That's going to be the shape. It's going to be square-based bipyramidal. So I have a note here. It says there are 6 sockets on the central atom, 2 polar and 4 square planar. The sockets contain all bonded pairs of electrons, so that's going to be important. Repulsion dictates that all angles will be mainly 90 degrees mutually perpendicular between all adjacent atoms. So that will give you an idea of what the geometry must be, and that will come out clearly in the clay model that you're making. So it's going to be square-based bipyramidal. And then you're going to put in your dipoles. Fluorine is clearly more electronegative than sulfur. So you're going to have your dipoles in. And if you look at your geometry, look at your clay model, you can clearly see you have bond symmetry and there is no polarity. All right, let's do aluminum trichloride and see what happens with that. So I have aluminum trichloride. That's going to be the shape I'm going to give it right now until I get some more information. It'll be trigonal planar. And I have a total valence of 24 electrons, 777 for the chlorine and 3 for the aluminum. And I have 3 bonds, times 2 is 6. So I have 3 outer chlorine atoms. Each needs 6 electrons to complete the valence. That's 18. So that's going to be subtracted from 24 along with the 6 bonded electrons. That's going to give me 0. So that will give me a 3 sockets, 3 bonded, 3 non-bonded. Remember, the parent geometry is going to be trigonal planar. So that's the shape. Now, are you noticing anything weird here with that shape? There's only 6 electrons around the aluminum. But remember, there are 3 sockets on the central atom, 3 trigonal planar. The sockets contain all bonded pairs of electrons. Repulsion dictates all the angles are going to be 120 degrees between all adjacent atoms. Aluminum has only 6 electrons. This is acceptable according to the rules. Check back on your sheet to check the rules. So, the geometry is going to clearly be trigonal planar. Now let's look at the dipole moments. And chlorine is going to have an electronegativity which is greater than aluminum. And so I'm going to put in my dipoles pointing towards the chlorine. We have bond symmetry, yes. We have no polarity. Next, we're going to look at nitrite. Don't forget the -1 means you're going to add an additional electron. There's an excess charge of 1 electron. So there's going to be your approximate shape. We'll make it linear for now until we get more information. Central atom is going to be nitrogen, so it's going to need at least 8 electrons. 5, 6, 6, 1, that's 18. Don't forget you have to have a total of an even number for this to work, and that extra 1 electron gives you that. And then we're going to have 2 bonds, so that'll be 4 electrons in the bonds that have to be accounted for. And then we're going to have 2 outer atoms, so that'll be 12 electrons. So 18 minus 4 minus 12 is going to leave you with 2, or 1 non-bonded pair to be placed around the central atom. So that's 3 sockets, 1 bonded, 1 non-bonded. And don't forget, you have 2 shapes like this. You have a bent with 1 pair and a bent with 2 pairs of electrons. Let's look at a note. It says there are 3 sockets on the central atom, 3 trigonal planar. The sockets contain 2 bonded pairs and 1 non-bonded pair of electrons. Repulsion dictates the angle will be less than 120 O N O because of that non-bonded pair pushing things closer together. So that's going to give a bent or angular geometry. Now we're going to look at the polarity. The electronegativity of oxygen is greater than nitrogen. That's clear. Simply look at your electronegativity table, and then We have the bond symmetry, which is no. Polarity, yes. Again, they will not cancel. Now we have perchlorate, -1, polyatomic ion, and you're going to set it up like this, and you're going to possibly guess that it's tetrahedral, and let's just simply go through it. I'm going to leave you alone, see if you can get these answers yourself. Don't forget to put things on pause. If you have a question, you want to write it down, see me in class, or try to predict what the next slide will be. So by now you can see that there are 0 electrons left over. There's going to be 4 bonds, no non-bonded pairs, and you're going to have a regular geometry. It's going to be tetrahedral, and there's not going to be a problem. You're going to have 109.5 degrees among all of the angles, and that's the end of it. There's your note relative to the angles. There are 4 sockets on the central atom. The sockets contain 4 bonded pairs of electrons. Repulsion dictates that all angles will be 109.5. That's the oxygen, chlorine, oxygen angles. And it's going to be tetrahedral. You're going to put in your dipoles, but as in a vector addition problem, they will all resolve to 0. There's your final shape with your dipoles. So it will be no polarity and yes to bond symmetry.